session. Session. um, the first talk will be by Shruti Hedge, our PhD student, who works under the guidance of Professor Attikari. Was my pronunciation correct? Good, okay. She will talk about the problem of Ruderman.
First, I'd like to thank the organizers for giving me this opportunity. I'll be talking on a problem of Ruderman. This problem was posed by Ruderman in 1974, and the problem is still open. I was we were looking at a problem connected to this problem. In that connection, I had read this paper, and I thought this is a good topic for this presentation. So let us start with an easy observation. 2 power 1 minus 2 power 0, if we consider that, we will be focusing on the powers 1 and 0. So initially if we start with 1 and 0, that will divide 3 power 1 minus 3 power 0, obviously, right? 2 power 1 minus 2 power 0 is 1, so it will divide that. And it will divide a power 1 minus a power 0 for all positive integers a, trivial. If I change the powers to 2 and 1, 2 power 2 minus 2 power 1 is 2. It will divide 3 power 2 minus 3 power 1, 6. In fact, it will divide a square minus a for any a, because a square minus a is 0. Okay? Again, 3, 1 is also it is happening. So the question is it always happening? Does this always happen? This was the question posed by Ruderman. Show that every pair of integers m and n such that m is bigger than n, for which 2 power m minus 2 power n divides 3 power n minus 3 power n, it also happens that 2 power n minus 2 power n divides a power n minus a power n for all positive integers a. In other words, if I write a as the set of all pairs mn such that and b if a and b are sets like this, then b is always a set of a, right? The question is, Ruderman's question is to show that a and b are equal. So in response to that question was posed in American Math Monthly. So in response to that question, Wallace proved one theorem, which is like here he gave a characterization for all pairs of integers mn, for which this relation here I have written in terms of n and k. Here k is nothing but m minus n, where we had in the previous mn we had, here it will be k. K is nothing but m minus. So this is a characterization for the second problem, second relation of Ruderman to happen. So let k be positive integer greater than or equal to 2, and let us write k as 2 power s into 2 t, where t is odd. All the even part we are separating, and 2 power k minus 1 is factorized as p1 power e1 up to pr power er. Pi's are distinct primes. Then this happens 2 power n into 2 power k minus 1 divides every a power n ak minus 1 if and only if these two conditions hold. The pi of pi power ei, where pi is Euler function, it should divide the k, and that should happen for every I, for every prime factor of 2 power k minus 1. And the second condition is that this n should be greater than every ei, every power in the prime power factorization, and it should be at most s plus 2. This is the characterization given by Yales, but this is only a characterization for the second one, second relation. There was an old paper of Schingel. This paper of Schingel it has nothing to do with this Rudderman's problem. But there is a result in that which was used by Pomerance. The result is if k is any integer other than I showed in the first. These three are the trivial examples I have given. We will talk more about it. If k is not equal to 1, 2, 4, 6 and 12, then there will be a prime factor for 2 power k minus 1, which will be at least 2k plus 1. Right? This is the result of Schingel. We can use this in Wheeler's theorem and get something I am going to tell. Okay. Suppose k is not equal to any of these, right? Then there is a prime factor which is greater than 2k plus 1. Right? For that prime factor here, the first condition will not hold, right? For the first condition to hold, pi minus 1 must divide k. But if pi is already greater than or equal to 2k plus 1, it cannot divide k. Therefore, if k is not equal to any of this, the first condition will not hold. That means the second relation of that Rudderman problem will not be satisfied. That means there will be an a for which 2 power n into 2 power k minus 1 will not divide a power n, a power k minus 1. So what we can say, for second relation of Rudderman to hold, that relation to hold, k should be equal to 1, 2, 4, 6 and 12. Right? It should be equal to one of these values, where k is nothing but our m minus n. So in the original statement, m minus n has to be equal to 1, 2, 4, 6 or 12. Is it clear till now? Okay, suppose that is happening, that 2 power n, 2 power m minus n minus 1 is dividing every a power n minus n minus 1. Then it should happen for in particular 3, right? A is equal to 3. And if this is happening, then 2 does not divide 3 power n. So 2 power n has to divide the second factor, 3 power m minus n minus 1. Right? And since m minus n is already bounded, we can also say that n is also bounded. So both m and n are bounded. And this was observed by Carl Pomerance after Wheeler's theorem. So what we have said now, that in the question of Rudderman, the second condition can hold only for bounded integer pairs, Mn. And the same result was obtained later independently by Sunda and Zhang. They were not aware of this discussion, I suppose, that they independently proved almost using the same arguments. With little calculation, we can show that these are the this is the exhaustive list of those pairs which satisfy that second condition of Rudderman. How do we do that? We know k can be equal to 1, 2, 4, 6 or 12. Put the values of k here, factorize 2 power k minus 1. You get pi's, ei's and s, right? Using the second condition, you can get an interval where n belongs. Once we get k value, once we have ei's and s, we can use the second condition and that will give you the values of possible values of n, actually exactly the values of n, right? So you get all possible pairs from this theorem and from those observations. So these are the 14 pairs that satisfy that condition. So the next question is, what happens to the first one? We have said that second condition is satisfied only by finitely many integer pairs. What about the first one? Ramamurthy and Kumarmurthy, they proved that the first condition is also satisfied only by finitely many m and n. But this also still has not solved Rudderman's problem, if you can understand that. We will talk more about why it does not. We will talk more about that. Let us see, the proof is straightforward. So let us see the proof of this one, assuming some bigger results right now. Later we will talk about it. So fix an epsilon in the interval 0, 1. And suppose Mn satisfies this relation. Then we can write 2 power n minus n1, 2 power n minus n minus 1 as a into b, where separating a will be all the 3's in that number and b will be number co-prime to 3. Right? Then b has to divide GCD of the two numbers, 2 power n minus n minus 1, 3 power n minus n minus. Why? Because b is already a factor of the first one, and since b is co-prime to 3, it has to divide the second, right? Now, for now, as I told, we will assume this result and we will talk about this result later. So what does this result say? For the epsilon we have taken, the GCD of 2 power k minus 1, 3 power k minus 1 has to be less than or equal to some constant into 2 power epsilon k, where constant exists, right? This constant depends on epsilon. And since we had b was dividing GCD, so it has to be less than or equal to that GCD, and in turn GCD is less than or equal to this one. So, and AB, since AB was equal to 2 power m minus n minus 1, and it has to be at least greater than or equal to half of that. So you get a lower bound for A in terms of m minus n. Is this clear? The idea is to get an upper bound for A in terms of m minus n so that it is bound. Since we have A is 3 power r and it divides 2 power m minus n minus 1, you can say this congruence holds. And 2 is a primitive root modulo 3 that we know already. 2 is primitive root modulo 9 we know already. We can use induction on R and we can prove that 2 is a primitive root modulo 3 power r for any r. So what happens then? Pi of 3 power r, it should divide m minus n, right? And pi of 3 power r is 2 into 3 power r minus 1. You can adjust that in terms of A, and that will give you the upper bound for A. So using those two bounds, we have this way. The left hand side is an exponential function of m minus n, and the right hand side is linear. So if this has to happen, m minus n has to be bounded. Right? And again, since we had minus n such that this was true, this 2 power n has to divide the second factor, 3 power m minus n minus 1. If n minus n is bounded, n is also bounded, right? So we can say that m and n are bounded such that 2 power m minus 2 power n divides 3 power n minus 3 power n. The first relation is also satisfied only by finitely many m and n. But the question is, how finite, right? We are saying that m and n are bounded, but we cannot give an effective bound for m and n because the constant that is used in this assumed result, is ineffective. Ineffective means it cannot be computed, it cannot be calculated. Right? It depends on epsilon, but cannot be calculated. As a result, we cannot say what are the bounds on m and n. Therefore, the problem of Ruderman is not solved. If we had bounds, we could manually calculate, or using some computer programs, we could check. What we want these n to coincide with that set of 14 pairs we had, right? So we could calculate manually if we knew the bond, but since we do not know the bond, we can only say they are finite. The problem itself is not solved, even by this. So we have assumed this result now. So let us talk something about this result.
14 parts satisfy B, right?
Yes, sir.
So the 14 parts we can check the
14 pairs, of course, they satisfy A. Yeah. But if there is any other pair, we don't. B is anyway a subset of A. That will be true for A is equal to 3 also. But if there is any other pair, we don't. And I think up to 1900 or something n value, they have checked, it is not there. But so this is the result that we assume. It was proved by Bujo, Horvaja and Zanier. And the statement goes like this. If A and B are multiplicatively independent integers, we can assume A and B are co-prime also. Then for given epsilon greater than 0, For sufficiently large k, the GCD of a power k minus 1, b power k minus 1 is less than a power epsilon k. Or equivalently, the statement that we used, right? There exists a constant such that this is happening. This theorem was proved using subspace theorem. Ranga sir has already stated and explained subspace theorem. I'm stating it for the sake of completeness. We don't have to try to understand the theorem itself, because we will not be looking at the detailed proof of that theorem, previous theorem. We can only, it is sufficient for us to only understand what this theorem is giving us. Right? So what we have in this theorem is, we have a set of absolute values, finite set of absolute values, including the infinite absolute value, Archimedean absolute value, and we have a collection of linearly independent linear forms. Then, if every solution for this inequality, or every n tuple which satisfies this inequality, will be contained in a finite union of proper subspaces of q power n. That is the statement of the theorem, right? If we look at the sketch of the proof, I think it will be clear. So what we want to show now, that GCD of a power k minus 1, b power k minus 1 is less than a power epsilon k for sufficiently large k, right? That we want to show. Suppose that is not true. Yes.
That was already proved in say which previous slide.
This is the statement I am same thing. Here we assume that, and I told that I will be talking about it. Yes, it is for sufficiently large. Suppose k naught is that bound. After that, before that, whatever is there, you take the constant. So yes, we have to show that this is happening. There is a k naught after which that is happening. So I am assuming on the contrary that is not true. Then what should happen? The set of all k for which the other side inequality greater than or equal to is happening has to be infinite, right? It is not finite. Then after this we define linear forms suitably. I'm not defining the linear forms or doing that calculation. We have to define the linear form suitably, and we take S of course to be all prime factors. I had to write union infinity, I forgot that. All prime factors of A and B. We are taking S and the linear forms suitably. Okay. Then what we do, from every k we define some n tuple xk, and we show that all those xk's will satisfy that inequality of the subspace theorem. Then we can use the subspace theorem, and we can say that all those elements have to be in a finite union of proper subspaces, and we can pick a particular proper subspace, and that will lead us to the contradiction. Right? That also has to picked a proper subspace also must contain infinitely many elements of x, and that will lead us to contradiction. Okay, that is the sketch. So you can see, since this theorem itself, subspace theorem itself, is ineffective, the bond on k that we are getting is also ineffective. Right? This discussion, what it gives is that why I am discussing this is to show that the constant we are getting, the bond we are getting on m and n are ineffective, right? Because of this theorem. Sorry? Those I have not, those here, whatever solutions we need, no, that I have called as the set X, the solution set X. All those elements which satisfy this inequality, those are small x. I have not defined or shown those things. I am just saying that has the same size as our set K. That is important. So here the constant being ineffective, we cannot say the bond, we cannot compute the bond. But Murthy and Murthy, they gave a a suggestion to alternatively use ABC conjecture instead of ABC conjecture and get another analog of Pujo and others result. So ABC conjecture is this: for any epsilon greater than 0 and mutually co-prime integers a, b and c such that a plus b is equal to c, this inequality is true. Maximum of the modulus values has to be less than, there will be a constant k epsilon, kappa of epsilon, it will depend on epsilon, and it will be computable according to effective version of ABC conjecture, and into this, the last part, product of P such that P divides ABC, it is called radical of that product ABC, and the power is 1 plus epsilon. This has to satisfy, so this has to happen, this is conjecture, right? So we can use this and find a version, similar to Bujo's result, we can find a result. And how can we do that? We can just take the GCD to be D, and 2 power k minus 1 will be equal to D into U for some U, and 3 power k minus 1 will be equal to D into V for some V. And this U and V have to be co-prime, right? Now you just multiply those 2 power k minus 1 into V, that has to be equal to 3 power k minus 1 into U, obviously, and that will give us this relation. It is in the form A plus B is equal to C, right? And A and B and C here will be mutually co-prime because U, V itself are themselves co-prime. And now we can use ABC conjecture and do some calculation, and that will give us the required form. So once we have this now, since we have assumed ABC conjecture with finite, effective version, the constant we are getting here will also be effective, right? It will be computable. Now we can use this result in place of that assumed result in our main proof, and that will give us effective bounds on M and N. The two problems, there are two, if you have observed, there are two problems that arise from the Ruderman question. One is this, right? What about this one? Here is we have proved that, we have seen the proof that this is finite, A is finite, right? The question is, what about this, is it specific to 2 and 3? Can we generalize it? That is one question. Will it still be finite? And another question is it specific to 2 here? Will B be still finite if we change 2 to some other integers? So I am talking about those two problems here. And in the first one, this was generalized. Not only we can change 2 to any other integer, we can in fact take polynomials and it will still be 2. What I mean to say is, suppose A1 up to AK and B are some integers in some number field, then this can happen only for finitely many k tuples, right? This can happen for only, and this should not be equal to 0, that is also our assumption. If this is equal to 0, then all our discussion becomes. So this also happens, not just 2 and A here, it can be any polynomial, and this polynomial for a particular value divides general polynomial for all z if and only if for only finitely many k tuples. This was proved in the first article. Is this statement clear? In particular, what we have here is when this polynomial ai zi z power ni, this is nothing but our a z power m z power n. or we can say n1, n2. In particular, if we have this is nothing but Rudamann's second part. So this is a generalization, and in the last one, this was also generalized. Here also we can change 2 and 3 to any co-prime integers, then also this is true. There will be only finitely many mn such that that happens, that a power m minus a power n will divide b power n minus b power n, right? And it is also generalized to imaginary quadratic fields. So those are the generalizations. Sorry.
Like the two and like two co-prime things.
Hmm.
Even the polynomial version is
No. Only if alpha, beta are co-prime integers, then alpha power n divides beta power n only for finitely many integers. That is not. And the proof is similar to this proof of Murthy and Murthy. They use subspace theorem, but we will need some more arguments. The result of Bujo, that is true for any A and B, co-prime A and B, right? So that they can use directly, but if we can recall that second part for second upper bound for A required that 2 was primitive root modulo 3 power r. So that has to be tackled here using some.
Thank you for the interesting talk.
Not be plus or minus one.
Where?
It's A1 is
Here.
here.
This is what?
Plus or minus one.
No. They can be any integers from the number. They are any integers from number field k. Any number field. And only in beta we need to be unit, so that if beta is equal to 1, k is equal to 1, then it will be trivial to, it will be for infinitely many. To avoid that, we assume that beta is unit, and these can be any integers from k.
It's an effective version of ABC conjecture. K, kappa epsilon. It should be computed.
What is the effectiveness?
Yeah, I mean, why is it?
Oh, this is usual, sir. This
Yeah.
Baker's version they have used, and from that Baker's version they derive this. Baker's version.
But what is the K, kappa epsilon? That must be
That
from
depend. There is some dependence. I don't know what is that dependence.
Baker has refined this for number of it as well as KBC conjecture in terms of effectiveness using this that way.
Yes, sir. Yes, sir. Exactly. That is why the problem is still open.
Plates.
No. This is a conjecture. They cannot. There is no point in using this.
They call it XYZ conjecture. So rather than gravity. It's just they have one of the
Sorry. Which one to happen? Here. This n1 to nk. No, not n star, it is n power k. K tuple. Sorry, my k looks like star. Shamik sir was asking if the version was effective. This version generalization, since again they use Schmidt's subspace theorem, it is not effective again. But this is effective. This generalization is effective. The second part, generalization, which is already solved in the trivial case also, that is effective. But the first part, which is ineffective in the trivial case, is also.
There, but astronomical constants.
But I think, sir, even that is not useful here because this was done in 2003. Even then, they did not use that. And if from what I understand, even in the proof, it is not possible to use same proof. At least is not working.
No, the number of spaces they count.
Yes,
That
sir.
is astronomical constant.
Okay.
You're not able to use it.
Yeah, let's thank the speaker again. Of Professor Shamik Paul. I hope I got the pronunciation right this time. Good. Okay. He speaks about smooth weighted zero sum constants. Yeah.
Am I audible? Good afternoon, everyone. I will be talking about some zero sum constants which are currently remarkable area of research. My talk is about a new zero sum constant. Before starting my talk, I should mention that the word smooth in the title and in the subsequent slides has no connection with the calculus, whichever we know smooth, word smooth related. It's only additive number theory. So throughout the slides, any subsequence, we mean by a subsequence we mean it's a non-empty, and we will see weight set later. So weight set also non-empty. First we will start with a simple application of pigeonhole principle. So if we fix a sequence of length n, then considering the partial sum, sequence of partial sums, so there are n partial sums, and by using pigeonhole principle, one can easily come up with a subsequence which terms add up to 0. And we are defining zero sum sequence, that sequence which terms of which adds to 0. Okay. That means the earlier observation says that any sequence of length n has a zero sum subsequence. Next, Davenport constant, which is well studied constant in this additive combinatorics area, which is defined as the least number such that any sequence of that length is forced to have a zero sum subsequence. So the above observation again shows that n is an upper bound, as any sequence of n length has a zero sum subsequence. So Davenport constant is bounded above by n. Next, we will consider the weighted version like other areas also. Here Podigari sir and his collaborators have started first weighted version. So here weighted version, the definition is almost similar. Difference is that the ordinary sum is replaced by weighted sum. So weights are from some weight set A, and similarly to more restrictive constants are weighted Gauss constant, which demands not only subsequence, it demands subsequence of length n, specific length n. Okay, and there are this constant is quite new, so it demands zero sum subsequence of consecutive terms. Now we will see the main definition, smooth weighted zero sum sequence. So a sequence is smooth A weighted zero sum sequence if there exists a k tuple such that the sequence weighted combination of the sequence is 0 together with the sum of the coefficients, mean sum of the weights is also 0. This is extra condition. So let us take an example. So if we take a weight set 1, 2, 3 subset of Z6, and if we consider sequence 1 minus 1, then it is clearly a smooth A weighted zero sum sequence, as the ordered pair 3, 3 ordered weight pairs 3, 3 does the work, as its sum is also 0 and it gives weighted sum of the sequence is also 0. But if we consider the same sequence in Z5, it is not smooth. It is zero sum, but it is not smooth. Zero sum, it becomes zero sum with 3 pairs 1, 1, 2, 2 or 3, 3, but it is not smooth as the sum of the weights is not 0 in Z5, as it is even. This smooth zero sum sequence has a special character that unlike normal zero sum sequence, it is invariant under translation. So if we translate a sequence by a number, then it remains smooth. So the advantage is that in the next some for some weight set, it will be easier to handle the sequence as translation, as we can translate. So we can assume that in any sequence 0 occurs mostly, 0 occurs maximum times. Next, the 3 constant, weighted Davenport constant, weighted Gauss constant and weighted consecutive ones. So 3 smooth version. So weighted A weighted zero sum subsequence is replaced by smooth. All 3 definitions are same as weighted versions, only the difference is that smooth is added. Okay. Next we will see some values and general bounds. Before that, from this definition one can easily calculate the easily get some relations between these constants, smooth versions. So dA bar lesser equals to A bar, because A bar it demands subsequence of length n, smooth zero sum subsequence of length n, but dA bar there is no restriction. So obviously dA bar lesser equals to A bar, and relation with the previous weighted versions. So obviously here there is more restriction, so it will be greater than equals to before the weighted version. So d a bar lesser equals to e a bar. Now the celebrated EGZ theorem, which states that if we take any sequence of length 2n minus 1, then it has a subsequence of length n such that sum of the terms is divisible by n. So in terms of Zn, this means that any sequence of length 2n minus 1 has a n length zero sum subsequence. So as a corollary, we will get e a bar lesser or equals to 2n minus 1. So if we take any sequence of length 2n minus 1, by the EGZ theorem, obviously there exists a n length zero sum subsequence. Now, so here a weight set can be any non-empty set. So suppose as it is non-empty, so obviously there exists some a. So as x1 plus dot 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 plus xn equals to 0, so obviously multiplying by a, it will remain same 0, and the sum of the coefficients is also 0 as it is na. So it follows that T is a smooth zero sum subsequence of length n, and that proves that the upper bound. So this celebrated EGZ theorem also gives upper bound for the weighted version, previous weighted version, and here also it gives the upper bound. Next we will calculate upper bound for CA, the consecutive ones. So it is n square. So first let us take a sequence of length n square. So we are taking n partial sums so that we can use Pigeonhole principle. Obviously we need at least n. So by Pigeonhole principle, if some yi is 0, then obviously we get some subsequence of length multiple of n, and if all yi are non-zero, then obviously some yi equals to yj, there exists yi not equals to j such that yi equals to yj. That means there we can get a subsequence of length of multiple of n. And now like previous one, here also as we get subsequence of length multiple of n, so by multiplying a weight, obviously the weighted combination is 0 and the sum of the weights is also will be 0. Okay, fine. Next we will consider the most trivial weight set, which is 1. So here one observation is that a zero sum sequence is smooth if and only its length is multiple of n. It's quite easy proof. So one weighted zero sum sequence means its sum is 0 and coefficient is as it is 1. So k times 1 will be 0, that is k, that means k is multiple of n. Okay. So this proves the lemma. Next, for this weight set, we get the upper bound as the constant for both d and e. Actually d bar lesser equals to e bar. So e bar lesser equals to 2n minus 1 means 2n minus 1 is upper bound of d1 also, d bar also. For the lower bound, consider the sequence n minus 1 zeros and n minus 1 ones. So first of all, uh, as the weight set is 1, so any zero sum sequence cannot contain 1 firstly, because there are n minus 1 ones, so we cannot get any zero sum among the ones, so it must contains 0. It must contains only 0, okay, because few ones will not give any zeros, so the subsequence must be in the 0 part only, but 0 also there, zeros are also there n minus 1 times, so that means there will be problem in the coefficient sum. 0 weighted sum is 0 obviously, but the problem will be in the second condition, that the sum of weights is 0. Here weights is 1, so that is not possible. Okay, so this proves the lower bound to n minus 1. Next, the for C bar also, the upper bound is the lower bound. So for the lower bound, let us take the sequence of zeros and ones, where 1 occurs n minus 1 times. So here also, here obviously there is fact of consecutiveness. So any zero sum subsequence cannot contain 1. So it must contains only zeros, but again, like previous one, it is not smooth. Okay. Next, we are considering the all non-zero weight set. So here first simple lemma, if we take two equal terms, then obviously that gives a smooth zero sum subsequence, as 1 and minus 1 are there in the weight set. Similarly, if we take three distinct terms, then it is also a smooth zero sum subsequence of length 3. As if we take xyz, the sequence as xyz, then considering the weights y minus z, z minus x and x minus y, we get smooth weighted zero sum. Okay. So we will use in the next slide these two lemmas, that if two equal terms, if there are two equal terms, then we will get two smooth zero sum subsequence of length 2. If there are three distinct terms, then we will get zero sum subsequence of length 3. So for the proof of the Davenport one, it is constant is 3. So firstly, for the lower bound, the sequence 0 1 has no smooth this weighted zero sum subsequence. So obviously that means that it is greater or equals to 3. And for the upper bound, if we take a sequence of length 3, then there are two possibilities. Either sometimes repeats, so then we will get smooth subsequence of length 2, and the last possibility is that the three terms are distinct, then also we get smooth weighted zero sum subsequence of length 3. Okay. Fine. Next, for the consecutive ones, the sequence 0 1 0 has no smooth weighted subsequence of consecutive terms, and for the upper bound, let xyzw be a sequence of length 4. So if there are two consecutive equal terms, then we are done. if there are 3 consecutive distinct terms, then also we are done. So we are left with the case xy xy, because uh, no times repeats back to back, okay, and no 3 terms are no consecutive 3 terms are distinct. So that means we are left with xy xy, and and as 1 minus 1 is there in the weight, so we get 4 length smooth subsequence, sequence. Now we will consider a interesting theorem in number theory, which is Chevalley-Warning theorem. It is on a finite field. So it states that if we take some system of polynomial equations with sufficiently many variables, such that the number of variables is greater than the sum of total degrees of the polynomials, then it says that it has not only solutions but number of solutions is divisible by the characteristic of the field. So here, as we are taking ZP, so obviously number of solutions is divisible by P. We will apply this theorem as we taking ZP, that means we will take different weight set QP. Okay, QP means the unit square. Do you know? Here. If yeah. If there is one solution, then it is multiple of P. So the weight set QP means it is x square such that x belongs to UP, unit square, all set of unit squares. So for that weight set we are calculating d bar. So for 3 mod 4, the constant is 5. So for the upper bound, let us take a sequence of length 5 and consider the following system of equations. So here it satisfies the hypothesis of Chevalley-Warning theorem, as the sum of total degree here is 4 and the number of variables is 5. So obviously there exists solution, obviously 0 is a solution, so there exists a non-trivial solution. That means sum of Bi will be non-zero. Now we are taking T, we are taking a subsequence T containing those xi such that the I for which Bi not equals to 0. If some Bi2, Bi1 is non-zero, then we will take xi1. If Bi2 non-zero, then we will take xi2 in the subsequence T. Then the subsequence T satisfies the first one, that means the QP weighted combination is 0, and the second condition implies that the sum of the weights is also 0. So the upper bound is done. Now for the lower bound, we know that for P congruent to 3 mod 4, minus 1 does not belongs to QP. Okay, it is if and only if P congruent to 1 mod 4. Now using the fact that minus 1 does not belongs to QP, we can show that the sequence 0 0 1 1 has no smooth QP weighted zero sum subsequence. First of all, as minus 1 is not there, so there will be no, means 2 1 1 will be not there in the zero sum subsequence. So it must contain zeros, only zeros. but there will be also problem as -1 is not there in the cube. So that's why the constant is 5. One. Because if 1 is 0, then for some and if we take a1 equals to minus a2, that means -1 equals to a1. This will contradict that -1 belongs to QP. Okay. For P congruent to 1 mod 4, the upper bound is same. With the same procedure, we can show that the upper bound is 5, and for the lower bound, we can consider 0 and it is between 4 and 5. Okay, now I have not given in the slides for the, as we have not get the constant, so it is between 4 and 5. Okay, upper bound will be in the same process by using Chevalier-Warning theorem. 0, 1, 1 is the extremal sequence. Next we will calculate E bar QP. So again, using Chevalier-Warning theorem, we can get an upper bound. For the lower bound, we have a result of Odhikari sir and Roth, that EQP equals to P plus 2. So, and E bar QP greater equals to EQP. From that we get lower bound, and for the upper bound, taking a sequence of length P plus 4, we are considering the 3 equations. So here also the equation satisfies the hypothesis of Chevalier-Warning theorem, as the sum of total degree is 2 plus P minus 1, so it is P plus 3, and number of variables is P plus 4. So, and 0, as 0 is a trivial solution, so there will be a non-trivial solution. Now we are taking a subsequence T like previous one, those xi such that bi not equals to 0, corresponding to which bi not equals to 0. Now the third equation, if we put the non-zero bi in the third equation, then we get 1 plus 1 equals to 0. So that will be that means that the length of T will be multiple of P. Okay, as Z1 power P minus 1, it will be 1 if we put a non-zero bi. So we get the length of T as P, as the length is P plus 4, so multiple of P means only P. Now the first equation gives that the weighted combination is 0, and the second equation gives that the weighted sum of the weights is also 0. So this gives the upper bound. Okay, and for lower bound, we are using previous result. Now we will prove that the constant is actually P plus 2, and means E bar QP equals to EQP, whichever we have got for the weighted ones. The smooth ones also the constant is same, but the upper bound is for only one, for p equals to 5, the constant is 9. For p not equals to 5, the constant is p plus 2. Only for 5 it is not working, but the upper bound is satisfying. Okay. Now these are the techniques for using for proving E bar QP equals to p plus 2. So first one, Chintamani Moria, which says that if we take 3 units, then the weighted sum set of the 3 units, QP weighted sum set of 3 units is whole ZP. Next one is the corollary of the Chintamani Moria result, which is that if we take a sequence of length at least, if we take a sequence of 3 non-zero terms, then it will be QP weighted zero sum sequence. And using this corollary, we are getting two sufficient condition for smooth QP weighted zero sum sequence. First one is that if we get some sequence such that its weighted combination is 0, but the sum of the weights is non-zero, then if we append to 0 to the sequence, then it will be smooth QP weighted zero sum sequence, applying the corollary. And next one is that, which one? Oh yeah, yeah. So the sum of the weights is non-zero. Let us take that is A. Now A is non-zero. This is vital. Now considering A 1 1, this sequence by the corollary, some QP weighted combination is 0. So let B1 to A plus B2 plus B3 equals to 0. Now so now we are claiming that T plus 0 0 is a smooth QP weighted zero sum sequence. So for T we are taking coefficient, so that's now sequence is this is, so we are taking the weights as B1, B1, B2, B3. So as AI is there. Oh yeah, B1, A1, B1, A2, B1, AK, B1. So that these weights are also in QP as B1 in QP, B1 is in QP, and AI are also in QP. So these weights are in QP, all weights are in QP, and if we take the weighted sum, then it will be 0, as here in B1 will be common. So A1x1 plus A2x2, this is 0 and this is 0. So and the sum of the coefficient will be B1 times A1 plus AK plus B2 plus B3. So this is B1A plus B2 plus B3. So this will be 0. Okay. Next one is, if we have a sequence with 3 terms 0 and 3 non-zero terms, then the sequence is a smooth QP weighted zero sum sequence. The proof is similar using the corollary. Okay. there is a theorem on restricted sum set by it was conjectured by Edwards and Helbron, but it is proved by Dias de Silva and Hamidun. It says that if we take a weight set of cardinality greater or equals to 2, then the restricted sum set is either whole group or it contains at least 2 times cardinality A minus 3 elements. So using this result, we are actually we will use these two result, last two result for proving E bar cube equals to P plus 2. Okay. So by that Dias de Silva and Hamidun result, we are proving a part of the first one. Okay. So if we take a P at P at least 7 and x1 S is a sequence with at least 4 non-zero terms, and we are assuming that also there are 2 distinct non-zero terms which are in the same coset of QP. Okay. Then that condition is we are getting that the weighted sum is 0, but the sum of the weights is non-zero. The proof is that first of all it has at least 4 non-zero terms and 2 distinct terms which are in the same coset of QP, either both are in QP or both are in UP minus QP. Sometimes some people call them as NP. Okay. So without loss of generality, let x1 x2 belongs to QP with x1 and x2 are distinct, and we are taking the subsequence T removing x1 and x2. Okay. Now by using Dias de Silva and Hamidun result, the restricted sum set QP plus QP is greater or equals to 2 into cardinality of QP is P minus 1 by 2. So it is P minus 1 minus 3, that is P minus 4. And as P is at least 7, so P minus 4 is at least 3. So there exists a unit in the restricted sum set. So that we are taking W. Now I have there is a result I am using for the last line, that W can be written as combination of T. There is a result that if P is at least 7 and a sequence has at least 2 non-zero terms, then any unit, then the weighted sum of that sequence contains any units, means whole UP is subset of that combination. Only the condition is that that sequence contains 2 non-zero terms. Okay, that is somehow I have removed. That will be using that we are getting the next line, that W can be written as the weighted combination of T, as we have assumed that S has at least 4 non-zero terms and we are removing x1 x2, that means T has at least 2 non-zero terms, so it satisfies the conditions. So W can be written as A3 x3 plus An xn. Now as my W belongs to the restricted sum set, so minus WB will be also there. For C Davenport. Minus W is also in the restricted sum set. That means there exists u not equals to b such that u plus b equals to minus w. Now we are taking some weights a equals to u by x1, a prime equals to that. Now all a prime, b and b prime all belongs to QP, as x1, x2 are in QP and uv are in QP. Now ax1 plus bx2 equals to minus w. Also a prime x1 plus b prime x2 so minus w is equals to minus w. Now we can get that a minus a prime x1 equals to b minus b prime x2 equals to u minus v, and as u minus as u not equals to b, that means and x1 belongs to QP, so it implies that a minus a prime not equals to 0. And now as x1 not equals to x2, so it follows that a minus a prime not equals to b prime minus b, and hence the sum of the weights a plus b not equals to a prime plus b prime. So here we are getting that minus w is written in two ways such that the sum of the weights are different. So we can minus, if we take w minus w equals to, this is also w equals to a3 x3 plus an xn, so minus w equals to minus a3 x3 minus an xn. Now if we take minus a3 minus an, so between these two representation, sum a plus as a plus b not equals to a prime plus b prime, so one of them will be different from this. So that means we will get some ax1 plus bx2 ax1 plus bx2 equals to minus w. Minus w means this minus a3 x3. This implies that ax1 plus bx2 plus a3 x3 plus n xn equals to 0, and this a plus, between these two one of them is different from that, so that means sum of a plus b or either sum of a prime plus b prime plus a3 up to an, that will be non-zero. That's we want. So we want the weighted combination is 0, but the sum of the weights is non-zero. Okay. So here the Erdos-Heilbronn means conjecture is important for this for proving the result. Now the main theorem, for the upper bound, lower bound is already there from E bar QP greater equals to EQP. So if we take a sequence of length p plus 2, then by Pigeonhole principle and translation invariance, we can assume that 0 occurs at least as the length is p plus 2. Obviously sometimes repeats, and we have seen in the earlier slides that from the remark that 0 occurs mostly, 0 occurs maximum times. So we can assume that 0 repeats at least twice. Now if S has at most 2 non-zero terms, then as the length is p plus 2, S has at least p zeros. then it is smooth zero sum. Okay. So we may assume that S has at least 3 non-zero terms. Now, in the case that S has at least 3 non-zero terms, suppose at least 3 terms are 0. So then S has at least 9 terms, as P is at least 7, so S has length at least 9. So there exist 2 terms. We can exclude 2 terms such that S minus AB has 3 terms 0 and 3 non-zero terms. Okay, by removing 2 terms we get such subsequence that which satisfies that the last the previous 2, the second one, if at least 3 terms 0 and 3 non-zero terms, then it is smooth. So as S has at least 9 terms, so there exists, we can remove 2 terms such that the remaining subsequence has at least 3 non-zero we are assuming earlier. Now it has at least 3 zeros. So we are done. If suppose at least 3 terms are 0, so that means at most 2 terms are means 0 can occur at most twice, and before we have said that 0 occurs at least twice, that means 0 occurs exactly twice. So let us take the last 2 terms as 0, and we are taking T is we are taking the subsequence T by removing the last 4 terms from S. Then T has at least 5 non-zero terms, as S has at least 9 non-zero terms. No. S has at least 9 terms. Yeah, the zeros are the last 2 terms only. So obviously the remaining one all non-zero, and at the length of T is at least 5, so that means all the terms of T will be non-zero. And now by Pigeonhole principle, there 3 terms will be in the 3 non-zero terms will be in the same coset of QP. So then there exist 2 distinct terms which are in the same coset of QP. Then this is satisfying the condition of the previous result. At least 4 non-zero terms and 2 distinct non-zero terms which are in the same coset of QP. Then we get the QP weighted sum is 0, but the sum of weights is non-zero. Then here we get for combination of T is 0 and the coefficient sum of coefficient is non-zero. Then attaching 2 zeros we get smooth QP weighted zero sum sequence, and as T has length P minus 2, as we are removing 4 terms from the P plus 2 length sequence, so we are attaching 2 zeros, so the length of T will be 2 and it is smooth QP weighted zero sum sequence. So it is the P length smooth weighted zero sum sequence. So that proves the upper bound.
smooth was given by somebody else, or you people only find smooth?
Smooth word.
Somebody else says it. Zero. It is possible to solve. But this is your definition.
And for the reference, one can the Google is just search smooth weighted zero sum sequence, then sorry, smooth weighted zero sum constant. You will get. It is not submitted, but it is in the archive. So
Yeah, good. And let's thank the speaker again.
One after the first time photos are taken, this way tell everybody to come.